Alright, so I've had a couple of requests out of the last homework set from 8.2 for number 40. This one is a little bit beyond anything we've done, so probably shouldn't have had it in the list, but it is kind of interesting. So if you look at these numbers here, so we got A1 is equal to 2, AN plus 1 is 1 over 3 minus A sub n, and they want us to show that the sequence is decreasing, show that it's bounded between 0 and 2, and then find the limit. You can't just take the limit of this thing straight away because it's not written explicitly. So it's defined with this recursive definition, which makes things a little bit more complicated. It is look at the sequence. You get something like this. You get 2, 1, 1, and you get 2/5, 5/13, 13/34, and so on, and you realize these are the odd numbered terms from the Fibonacci. So, or this is the ratio of the odd numbered terms from Fibonacci. So this is kind of interesting to see what this is going to go to. And it's going to take some work actually to show that it does go to something, and then to actually going to have to use a trick you've probably not seen before. Okay, so to begin with, let's first of all this is going to be using something called induction. This is to prove that we're decreasing and that we're bounded between 0 and 2. Alright, so what you've got to do is first of all consider kind of what they call the base case when you do induction. That is the case when you're looking at the first terms. So note that 2 is bigger than or equal to A1, which actually is 2, and that is bigger than A2, which when you calculate it is 1, and of course that's bigger than or equal to 0. Okay, so that's the base case. So we know in the first step that it's decreasing. Now what you got to do is now show that it's decreasing at any step along in the sequence, and that's what induction allows you to do. It's a little bit different than what you're used to, though. This is a proof, so it's going to take some doing. So let's pretend or suppose that we're in a situation where 2 is bigger than or equal to A sub n, which is bigger than A sub n plus 1, so that's the next one in the sequence, which is bigger than or equal to 0. And now we're going to show that it works when you have an n plus 1 here and an n plus 2 here, and then we can always get to the next one in the sequence. And so so we're going to go to the next slide, and now so we'll begin by multiplying that inequality we just had by -1. Now you'll recall from pre-calc, hopefully, that flips the order of your inequalities. Now add 3. So what I'm doing here is kind of backing into the definition of A sub n here. And what I'm going to back into is exactly what I want. Okay, this is kind of nice because on the left most side we have a 1. And then we have 3 minus a, that's less than or equal to 3 minus a sub n, which is less than or equal to 3 minus a sub n plus 1, which is less than or equal to 3. Very important to note here that this means that these guys are positive. Okay, because in the next step we're going to reciprocate, and that's going to flip the order of the inequalities again. But if they're not all positive, that won't happen all of that up, and you got to be super careful, remember, with these signs. Okay, so we reciprocate, everything's positive, we're okay. So 1 is bigger than or equal to 1 over 3 minus a sub n, which is bigger than or equal to 1 over 3 minus a sub n plus 1, that's an a there, sorry, which is bigger than or equal to 1/3. And let me just note that means this guy here, this is the definition of a sub n plus 1, and this is the definition of a sub n plus 2. So what we've seen is we now have this inequality, which is indeed almost what we needed. It's more than what we needed, actually. An important thing here is this side is bigger than 0, and this is less than or equal to 2. So if we know it is true at some point that an is bigger than an plus 1, then this step, this is what they call the inductive step, lets us conclusion here. So for all n bigger than 1, 2 is bigger than or equal to a sub n, which is bigger than a sub n plus 1, which is bigger than or equal to 0. And so this gets the conclusions we wanted. Thus, an is decreasing. It's decreasing, and it's bounded in this way. So 0 is less than or equal to a sub n is less than or equal to 2. So of course, and you know that the sequence has to converge. So that's great. But that leaves the question, converges to what? So what is the number? Now if you calculate it and you start watching the computation, you is settling down to a number. It's a 0.381966 and so on, but what in the world is that? So what we're going to do here is go back to our recursive definition, and this is a standard trick, but probably one that you haven't seen before. So go back to your recursive definition, and we're going to assume that we are at the limit, or assume a steady state, you might say. Let's assume x is the limit as n goes to infinity of a sub n. Okay? And then it's going to have to be that in the long run this is also true. X is equal to 1 over 3 minus x. And the question is, what is x there? So now you have an equation to solve. So multiply on both sides by 3 minus x. You see that? So we get 3x minus x squared equals 1. So just a quadratic. So x squared minus 3x plus 1 equals 0. So, aha, quadratic formula time, right folks? So x is minus b plus or minus square root of b squared minus 4ac all over 2a. So what you get is 3 plus or minus the square root of 5 over 2. And so now your question is, well, what about the plus or minus? It can't go to two things. Which one does it go to? Which one does it not? If you check out the plus one, you will get a number bigger than 2. Well, we just proved, in fact, it's substantially bigger than 2. And we just proved that this thing is smaller than 2 and decreasing, so it cannot go to a limit that is bigger than 2. So we're not going to use that one. So it must then that the limit as n goes to infinity of a sub n, that's what we called x, that is 3 minus the square root of 5 over 2. And then if you tap that on ye old calculator, you get 0.38196601125 and stuff. Okay, so that was kind of cool. And so this is very interesting too, because this is the limit of the ratios of the odd numbered terms in the Fibonacci sequence. So you see we had to do a proof to show that it converged. We did that by showing that it's monotone decreasing and bounded. And then we used this little steady state or limit assumption trick to figure out what the actual value of the limit was. Alright, well, hope you enjoyed that and hope that was insightful. No, this is not something I would ask you to do in a testing situation, but did broaden your horizons a little bit, I hope. Alright, thanks a lot.